In the next two lessons we're going to look at nuclear fission. First of all, we're going to look at the nuclear fission reaction, and then we're going to look at how a nuclear fission reactor works. So nuclear fission, as opposed to nuclear fusion, involves obtaining energy by splitting a nucleus, whereas fusion involves obtaining energy by joining nuclei. So we'll look at nuclear fusion in a later lesson. First of all, the nuclear fission reaction. In most cases, the fuel used for nuclear fission is uranium-235. Okay, so in order to access the energy stored in the nuclei, we're going to get it to absorb a slow-moving neutron. Now, we'll look at the technical side of this process when we look at the nuclear reactor in the next lesson. What happens when the uranium nucleus absorbs this neutron is it becomes unstable, and this causes it to split. Now, when it splits, it will form the nuclei of two new elements, and there are various ways in which this can happen. In this case, it's split into krypton-92 and barium-141. And when this splitting occurs, the crucial point is that either 2 or 3 more neutrons are released. These are more neutrons that have been released as a result of the split, and these neutrons will then go on to collide with more uranium nuclei, which will also split, which will cause more neutrons to be released, which will then go on and on and on, and this produces what is known as a nuclear chain reaction. And this will result in an absolutely huge amount of energy being released, which we'll take a closer look at in a minute. Okay, so you've got a huge amount of energy as a result of these uranium nuclei splitting. Now, there are two really big problems with regard to this type of reaction, or nuclear chain reaction. First of all, is that it's a nuclear chain reaction, and subsequently the reaction could very quickly get out of control, as these neutrons go on to destabilize more nuclei, which releases more energy, and so on and so on. And if you don't control this chain reaction, what you're going to get is effectively a nuclear explosion. So the chain reaction, first of all, has to be controlled. We'll look at how that happens in the next lesson. And the other problem is that these nuclei that are produced during the reaction, these are called the daughter nuclei, are usually in themselves highly unstable. And they're unstable because they've always got the wrong number of neutrons in their nuclei, and consequently they're highly radioactive. So one of the byproducts of this type of nuclear fission reaction is you get a whole load of highly radioactive nuclear waste composed of these daughter nuclei that are produced during the reaction. And this nuclear waste will eventually have to be removed from the reactor and dealt with somehow. Okay, so this is a brief summary of a typical nuclear reaction, and as with all nuclear reactions, we can write nuclear equations that go with the reaction. So let's look at the nuclear equation for this reaction. Okay, so we've got our slow-moving neutron colliding with the uranium-235 nucleus. That produces barium-141, atomic number 56, plus krypton-92, 36, plus 3 neutrons. So you'll notice that, as with all nuclear equations, the numbers have got to add up, and you'll find that 1 plus 235 will sum up to 141 plus 92 plus 3 times 1. Okay, likewise, the atomic numbers will also sum up so that this equation is balanced. Okay, and clearly the one thing we want to get out of this reaction is energy, so there's huge amounts of energy released. Okay, and typically the standard sort of comparison is that 1 gram of uranium-235 will provide the same amount of energy as 1,000 kilograms, that's 1,000,000 times this mass, of coal. Okay, so there are enormous benefits to nuclear power in that it produces a huge amount of energy, but there are problems as well in that, as we've just mentioned, this chain reaction could be potentially dangerous if it's allowed to grow out of control, and also, in terms of the radioactive waste material that's produced. Okay, so this isn't the only way in which the uranium can split. There are other ways. For example, you've got uranium-235 splitting into lanthanum and bromine 88 plus your 3 neutrons, which will then go on again to trigger more nuclear fission reactions. Okay, and so again, these products are going to be nasty. Bromine's bad enough when it's not radioactive, but when it's radioactive, it's even a whole lot worse. Okay, so these are products that have got to be gotten rid of somehow, and so that's a big problem for the nuclear power industry.